collision, probably. Okay, time to get started. Let's go over the record. I don't see Ryan or Amanda or Bridget. Oh, there you are. Okay, Bridget. Hannah. Reagan. Diksha. There's Hannah. Austin. Jaron. Toussaint. Yeah. Edward. James. Okay, just came in were Ryan and Reagan. So the people I still don't see are Amanda or Diksha. There's Diksha. Or Austin. There's Austin. Or Jaron or Edward or James. There's James. Not right now, no. Okay, we had a test yesterday, and the problem with the fire hose, everybody afterward was saying that one was not pleasant for them. I will go through and look at the scores, and if it turns out that is indeed a problem that should be discounted, I will act accordingly. And there it is. Okay, so we will continue with fluids. Just a few more things from chapter 11 before we start chapter 12. And I recognize there should have been a reading quiz for today, but in going over the test over and over and over again before the class, I didn't have time to make the potential test questions, or not potential test questions, different class, the reading quiz questions. So I apologize, there should have been one. So, yeah, oh well. Barometers. Barometers are something from chapter 11. A barometer is used to measure the pressure of the air in the atmosphere, and is often used as a bellwether to tell you if the weather is going to get better or get worse. So what we want here is to understand how a barometer works. So for the beginning of a barometer, barometers are usually made with mercury. I would have one hanging here, except for the mishap with my equipment and moving over here where we spilled some mercury, probably less than a teaspoon, spent $200,000 on remediation thereof, and by the time they got in to actually do the remediation, there was no mercury left anyway. So that's why we don't have any mercury things here. It's my fault. And yes, it's the EPA's way of making sure people get paid to do nothing, because that was the the outcome. Okay, so you usually use mercury. Mercury because it has two nice properties for a barometer. Property number one is mercury has a pretty big density. If I remember right, the density for mercury is 13.6 grams per centimeter cubed. Or compared to water, that's 13.6 times the density of water. Pretty high. Compared to gold, no, not so high. But it's a pretty dense material. Also beneficial for the purposes of a barometer is the vapor pressure of mercury is very low. That means it doesn't go into vapor very much. It stays mostly in the liquid form. Why is that important? Because to make a barometer, the first thing you do is you take this tube. Notice the tube is open on the bottom and closed on the top. And you just submerge it in the mercury and get it completely filled with mercury. I'm sure there's other ways of filling it with mercury, but that's the easiest way if you got plenty of mercury. And really, mercury isn't all that dangerous. We used to play with it when I was a kid. And look, I'm not crazy yet, right? The danger for mercury is, heavy metal poisoning. And as I understand things, the Mad as a Hatter saying is based on hatters who used mercury to steam the felt, I guess, of making hats. That's what I'm told. And so they were inhaling mercury vapor, and that's what makes them eventually go crazy. So that's, one of the dangers is that going crazy, blood pressure shooting up to, 300 over 200, something like that. Those are bad things that happen with heavy metal poisoning. I'm more worried about the crazy, obviously. Okay, so fill that tube up so it's completely filled with mercury, and then keeping one end in the mercury, you tip it up. So we have learned that if you make, if you have a depth D here in the mercury, that the pressure difference between the top and bottom is delta P is equal to rho of the fluid times G times that depth of the fluid, right? Well, if you have this column of mercury that's a height H, that same equation is going to apply. The pressure difference from the top and the bottom, well, the bottom is just held at atmospheric pressure. Is going to be the density of my fluid, in this case it'd be mercury, times G times that H. And so I can calculate the pressure of the atmosphere is equal to the pressure in the top plus the density of my fluid times G times H. So the atmospheric pressure is going to change linearly with the height of the column. But what's the pressure at the top? If I started with this thing completely filled with mercury, there was no air gap, right? Now when I turned it up, the weight of the fluid is going to pull down, but it will only pull down until you get to a pressure at the top of 0. Once you get to a pressure at the top of 0, remember pressure is the force per area. So when the pressure is 0, that means that the top of the tube is no longer pushing on my liquid. And then the column will just stay without touching the top. And so we have up here in the top what we call a vacuum, which is when the pressure is 0. Pressure can never be negative. It's always a compressive force. And so the minimum pressure you can get is 0. And once you get to 0, you just have a gap. Now, we like to say an air gap, but what ideally is that gap? What is in it? Nothing ideally. If you have mercury with a very low vapor pressure, there would be very, very little mercury gas in there. It would be very close to an actual vacuum. If you have water, which has a much higher vapor pressure, you'd have much more water vapor in that gap, so it wouldn't exactly be a pressure of 0. So that's why mercury having the low vapor pressure is beneficial. So in the end, after all of this, if the pressure on top is 0, then that means atmospheric pressure is just the density of the fluid times G multiplied by the height of that column. Now, just for fun, let's calculate what the height of the column would be if pressure atmosphere is equal to 1.013 times 10 to the 5th pascals. If that's the atmospheric pressure, that is the standard atmospheric pressure. Keep in mind that atmospheric pressure does go up and go down, and so that's not the pressure at any moment. Although in our problems, we will always use that number for atmospheric pressure unless told otherwise. So if that's the atmospheric pressure, then that should be equal to the density of my fluid times G times the height. So if I solve for height, density of the fluid, 13.6, and I'm going to change it to kilograms per meter cubed, which means just times 10 to the 3rd. Kilograms per meter cubed times G, 9.80 meters per second squared. And someone with the calculator handy, would you please calculate that number for us? I know what it is in theory, but I want to make sure that that's what the number comes out to be. Okay, so 0.760 meters. And a lot of you probably already knew this, right? I said I knew it because since 1 atmosphere will cause you to have a column of mercury with vacuum on top, have a height of 0.760 meters or 760 millimeters. One of the units for measuring pressure is millimeters of mercury. That's measuring how tall this column will be if you have vacuum on one side and atmosphere on the other. And so we have 1 atmosphere, which is 1.013 times 10 to the 5th pascals, is also equal to 760 millimeters of mercury. What's another name for millimeters of mercury? Torr. Right? Millimeter of mercury is the same thing as a torricelli, torr. So that's an easy measurement. Now, if you look at the old school barometers or even the information they give you on the news, what do they measure the pressure in? They say barometric pressure today is 29.5. That's inches of mercury. When you see the barometric pressures in numbers that are varying between around 28-ish to 31-ish, that's in inches of mercury instead of millimeters of mercury. Because while mercury is a good material to use, the infinite wisdom of our forefathers said, let's use these inches that we can subdivide in whatever units of 12 inches in a foot and 3 feet in a yard, and so on. Okay, now a couple important topics. What does it mean to have a vacuum? That means the pressure is 0. That's the minimum you can get. You can't get a negative pressure. So if you were to take this tube and lift it up so that it was lifted up so the bottom was here, and thus the top moves up to here, what would happen to the height of the column of mercury if I did that raising of the tube? It wouldn't change a speck because you had pressure atmosphere at the bottom and pressure vacuum on top, and the height that will have that pressure difference is going to be the same regardless of how I adjusted that column. Yeah?
So like you mean the height of the clear part there, the height of the volume of the vacuum stays the same?
The height, this height right here would stay the same.
And the tube moves
As the tube moves up or down.
More vacuum space now.
Yeah. Okay. Because there's no pressure in there, it just doesn't make a difference. Now, what if we use water in our barometers instead of mercury? What would be different? Yeah. I saw the recognition dawn with a little wry grin. You would have to have a pipe that is 13.6 times taller for a water barometer. So while a mercury barometer is less than a meter tall, a water barometer would have to be more than 10 meters tall. That wouldn't be very convenient, hence we don't use them. Also, what would be a drawback for using a water barometer? Yeah, you're not going to get a very good vacuum in the top, so you have that vapor pressure issue. All right, now let's have a clicker question. And the clicker question says, select 2, so this one should accept 2 correct answers. I hope I said it that way. 2 good reasons to use mercury in barometers. So you should put your correct answers and then hit enter. And I can judge by Reagan's answer that it does indeed allow you to put in 2 answers. I didn't screw it up. Anyone else sweating in here? You cold? I wish.
We can't come up with something cool to use instead of mercury that's not toxic.
We don't have an alternate, no. So we had answers were 6, 21, 19. There aren't many fluids that have that kind of density. And now if you look at this, all of these statements were true statements about mercury. Mercury does expand pretty rapidly when changing temperature. That's why we often use mercury in thermometers, because it expands rapidly when changing temperature. That actually is not a good thing, though, for your barometer, right? Because if it expands rapidly with changing temperature, that means that its density is expanding significantly with changing temperature. So the barometers are actually going to vary more with changing temperature. So that's definitely not a good thing for the barometer. You sometimes have to take the bad with the good, or that's the case. These two were the correct answers. Has a high density, so it doesn't have to be a very tall column, and it has a low vapor pressure. Okay, a hydrometer. Hydrometers are used to measure the density of water. Back when I was a little boy, our batteries in our cars, they were lead-acid batteries, but they weren't sealed lead-acid batteries. You had to put more battery fluid in. And how do you know if you need to put more fluid in? Well, of course, you want to measure the level, but another thing you did was you measured the density of the battery acid. And so you would have a little thing that would suck battery acid out of your battery and measure the density of the battery acid. And how we do that is with things like this, a hydrometer. So here's a hydrometer. It is a glass tube that has some lead down here at the bottom. And then it has a piece of paper that has numbers marked on it. It's hollow with lead. If it's hollow, what do you think it would naturally do? It would naturally float. Why would it float? Following what we've learned. Okay? The density of the entire thing is lower because you're mixing density of air with density of glass. That's why they have to add the lead to get it so it will sink more. I put this in here now. It floats, and I measure the density of the water. I need it to be vertical by looking at where the water level hits it when it's floating vertically. If the water is less dense, then the water has less mass per volume, and to displace the same amount, it's going to have to, if the water is less dense, then this is going to float lower. If the water is more dense, then it floats higher. And so that's how this works. I have a couple of them here. That one floats pretty high. This one is much more precise. It has numbers going from 2 to 1. Don't drop and break. Bad. Okay. And this shows that the density of our tap water here is very slightly less than 1 gram per centimeter cube. And then this one here is a homemade one. It's just a piece of wood. Wood floats. It's got some wire wrapped around to load it so that side will stay down and so that it will float something lower. And then it just has taped on a grid so that you can calibrate it and find how high that thing floats. And you can't really tell, but it floats pretty low. So that's how we actually measure the density of a fluid. We use something like this. Pretty simple device, simple physics. And it works perfectly for a class like this, where I know it seems pretty difficult. I mean, when you're learning this stuff, you got to admit, it's a little difficult. But this is the beginning level. So it gets a lot harder. That's what I'm saying. Okay. Talking about menisci. Menisci, that's the plural of meniscus. 2 examples there, mercury in glass and water in glass. With a mercury glass meniscus, you actually have the water level goes down inside of the tube, and you have a meniscus that is concave down, right? That's concave down, the downside is concave. Why does it do that? I've said it before, I said it like 3 weeks ago though. It's the adhesive versus cohesive force. In the case of mercury with glass, the mercury doesn't really like to touch the glass. It's a much higher energy for mercury to touch the glass. So the mercury will actually push down to try to avoid touching the glass. And that's what gives you, and that's because the mercury has a stronger force trying to touch other mercury. And so that's what gives you the concave downward meniscus and pushes the level down. Over here, water, the water has a strong adhesion to glass, and it pulls the water up because it's actually lower energy to go to a higher elevation but be touching more glass. Now I have a demonstration. Yeah, it didn't work out. I keep it down here because this thing leaks a little, and leaking's not good. So here I have water in different tubes. And what you notice about the water level, actually let me take a picture of this. Take a picture with all of my wonderful students in the background. I know you can't see it, can you? But you should see it now. Okay, so we have our water here. It's kind of hard to draw a horizontal line on this, but you notice that the levels are slightly different from one material to, or from one tube to the next.
Is it because they dripped out? Or...
Okay, I think, does that look about, okay, so we have different heights in there. They're all connected together. That black bar underneath is a manifold. I filled it simply by pouring water into this big one. So we have the same water all the way through. Which one is the highest? At least if my lines are drawn correctly, I did my best. It looks like this one here is the highest. Nice. I'm still in the line mode. It looks like this one here is the highest. This one here is about the same. These two over here are a little bit lower than that. And that one there, I don't have it full enough for that one to show as much as it would be nice to. The levels are different. Can you see any kind of pattern between those levels? Thinner tubes tend to go higher. The tubes over on this side are thinner tubes. The ones over here are thicker tubes. And then, of course, this is the biggest. And they're drawn up more in the thinner tubes. Why would they be? I think I have a picture before the next clicker question. Let's see. A picture that shows something like this, but the textbook picture instead of one I just took. I really think it's here. There we go. So here's a picture that's showing, now this is of course not a photograph. A photograph is easier to believe than a drawing made by the textbook. But it's illustrating that the smaller the diameter of the tube, the higher the level. Now what's the term that you've all learned to call this? Capillary action or capillarity. And the cause of this capillary action is what we were just talking about, the strong adhesion between the glass and the water. And if you have a smaller tube, the weight of the water for 1 column inch is less than if you had a bigger tube. So you're going to a lower energy by having more water touching the tube. With that lighter column weight, you can raise the column more to get to that energy balance. So the reason these narrow ones rise more is because the weight of the column is smaller. And so over here you see a comparison. If I had a magical material that was just like water except for more dense, it wouldn't rise as much because, once again, that would be a heavier column. So if I had identical columns, the more dense material wouldn't rise as much if it had the same cohesion, adhesion properties. Questions? Okay, clicker question, maybe. Why is capillarity more obvious in a smaller tube? Sometimes I wonder why I ask such obvious questions for this class, but in my astronomy class, I would get all of these answers. There are clearly some people who weren't listening every time I ask a question. So, yeah, there's different levels. Okay, everyone's answered. 5, 11, 5, 2. Might I assume you're mocking me? I'm going to go back to this picture here and let you discuss it with the people around you, just in case you weren't mocking me.
Can we consider the capillary action like a force acting upon it?
Well, there is a force that is Okay, let's try this again. So it is now open to retry. Okay. What's the correct answer?
B.
No, it's not B.
Oh.
It's A. The correct answer is the weight of the fluid in the tube is smaller, so that the upward force pulls it up higher to get to the lower energy. Remember, if it's heavier, you can't pull it up as high to get to the energy difference caused by the surface energy being lower. And yeah, I had said that as a direct quote, and I thought that everybody would just answer that. That's why I thought you guys were mocking me. Not good with quotes. Give me things I have to think about. Okay, moving on. The force is, I was just talking to Ryan while we were doing this. If you have a meniscus like this where it's upward, then the force between the wall and the fluid is going to pull the fluid in the direction parallel to the surface at the point of contact. And so here the wall is pulling up. And so you can pull up, a weight proportional to how strong that force is. And when it's smaller, it makes it more weight that you can pull up. Well, not more weight that you can pull up, but a bigger amount you can pull up because it's lighter. Question, go ahead.
So if you fill that thing with mercury, would it be the opposite?
Yep. If you fill it with mercury, it'd be the opposite. Okay, this is like my next to last thing, I think, on chapter 11. Breathing. We all like to breathe. Makes life easier for us. And we tend to think that, like, when you drink from a straw, you can suck stuff up in the straw, right? The answer is you can't suck stuff up. Even though that's what we say. What happens, what makes stuff come into you when you are drinking out of a straw? You decrease the pressure on top. Here's a straw. You have a liquid. You have pressure atmosphere pushing down here. Now, Pascal's principle says that pressure is distributed everywhere throughout the liquid. So if I stay at the same elevation, I would have pressure atmosphere right there. Come down lower, of course, the pressure gets bigger because you've gone lower. You put on the top of this your mouth. There's your lips, nose, whatever. Okay, and what you do is you lower the pressure, so it's pressure atmosphere minus delta P, where delta P is the small amount of pressure lowering you can get. Now, if you look at this, you have a higher pressure on liquid in that column from below, a lower pressure on top, which means you have a force pushing up on the bottom of it that's caused by atmospheric pressure, and you're pushing down still with your mouth, but your mouth isn't pushing down as hard as the atmospheric pressure is pushing up on that column. And so it comes up because the net force is up because you have a lower pressure on top. So the whole way we drink with the straw is reliant on us having atmospheric pressure. If you are in the International Space Station and you got your little sippy cup, because if you don't have a sippy cup, it's going to be everywhere, you can't just drink out of it. Because there's nothing to push it into you. Okay, I say that kind of false. Why is it kind of false? Yeah, they pump it up because otherwise you'd go. So, it's kind of false because there actually is about half an atmosphere of pressure in there. Why half an atmosphere? Well, it's going to be less likely to fail because you don't have as big a pressure difference inside and out. And if you need to do an extra vehicular maneuver, I think that's what they call them, then it's not as big a change in pressure that you have to deal with. So, because they pressurize it would still work some, but not as well. And if you were outside, if you were on your extravehicular activity, and you tried to drink out of your sippy cup, you would get absolutely nothing. Because you have a vacuum, nothing pushing anything up the little mouth thing on the sippy cup. And you can do anything you want. You're not going to pull anything in. Now, why do I talk about that here? Because how do we breathe? We breathe by basically, you pull the diaphragm muscle down, and it creates a bigger space in your lungs, which allows air then to flow, and it lowers the pressure, very small amount inside the lungs. So the atmospheric pressure is higher by 2 to 6 millimeters of mercury. So then atmospheric pressure pushes air into you. Once again, you couldn't breathe in outer space if you didn't have something to blow the air into you. And then when you exhale, of course, pull that diaphragm muscle up, pull in those intercostals, and you increase the pressure in the lungs so it's higher than atmospheric pressure, and you push the air out. So when we're when we're drinking, let's go with breathing. I don't know where my brain is. Eating and drinking, apparently. We're doing these by manipulating pressure so the atmospheric pressure either pushes air into us or pulls air out of us. Well, it doesn't. It's pushed out by our lungs. Okay, enough of that.
Just real quick.
Yeah.
When we're drinking with the straw,
Yeah.
we must be expanding the volume. We're like,
How are we what you're doing is you're to the simplest level, like if you're just doing it with your mouth, then you start with your mouth all closed, so there's very little gas in there. And then you open it up, so you have a much bigger volume. So for that gas to fill the volume, the pressure has to drop, and that's what allows it to come up. Yeah, I don't know about you guys, but when I was a kid, I liked to go to the bottom of the swimming pool with a hose and try to breathe through the hose. Not very easy, because the pressure difference my lungs are making not so big. Okay, a medical application. Let's say they want to measure what the pressure is in your spinal fluid. It's not cerebral spinal fluid at that point, right? It's just spinal fluid. Cerebral spinal is above the, I think. I don't know. I'm not all I know is that when you have cerebral spinal fluid coming out the ear, that's a bad sign. That's what they taught us in our EMT class, was how to check cerebral spinal fluid coming out of the ear, which should never ever happen, right? Okay, so if you want to measure it, first of all, you have to tap the spine, which brings up that epic movie, This is Spinal Tap. So they stick a needle into the spine and then just measure the pressure by using what we call a manometer. What's a manometer? Well, it's something that is going to have a height of fluid. You measure that height to get the pressure. So in this case here, you can see they're using water to measure the pressure, and they say that the pressure difference is 10 millimeters of mercury. How high should the water stand for a pressure difference of 10 millimeters of mercury? You can do this in your head. Multiply 10 millimeters by 13.6, and you would get 130.6 or 136 millimeters or 13.6 centimeters. Right? That was not a hard calculation. We could do it in our head. Because, why was the difference 13.6? Density of water versus the density of mercury. So what I did is I said the pressure difference is equal to rho of density, G times the height, rho of mercury. And mercury is equal to the density of water times G times the height of H2O. And then I just solved that for the height of water. So solving that for the height of water, and since the density of mercury is 13.6 times the density of water, that's why I just multiply by 13.6. So that's a way you can measure pressure. Now let's say we wanted to insert something into a person's spine. Like we're going to inject some kind of medication to make it so they don't feel any pain. In terms of pressure, how much pressure am I going to need on my injection? Say the pressure in the spine is 10 millimeters of mercury higher than atmospheric pressure. How much pressure am I going to need in my syringe to force something in? Higher than that. Not a lot higher, right? I don't want to, just shoot it in there super fast, but it's going to need to be a little bit higher, so there's a higher pressure pushing in than there is pushing out. Okay. I think that brings us to the end of chapter 11 material, starting with chapter 12. What's the difference in chapter 11 and chapter 12? Chapter 11 was all stationary stuff, static fluids. Chapter 12 is moving fluids. So we start with a basic continuity condition. Continuity, continuous. If I have a confined, continuous flowing fluid, I like to measure the flow rate. That's how much fluid per second is passing. And so I have here just a tube, and I have material going through the tube at speed v. So the flow rate here, this is technically the volumetric flow rate. That means it's the amount of volume that passes a certain place per time. So I would just put, here's the place I'm going to measure. And I measure for some time amount, delta t, and I can say, how much fluid passed in this time, delta t? Well, how would you determine the volume that passes in time, delta t? First of all, what's the equation for volume? A simple geometric. Okay, it's going to be the area. Since this is a cylinder, pi r squared is the area. And then he said height multiplied by the distance here of my column. Right, volume, area times the distance, or length times width times height if it was a cube, something like that. So I'm going to use that because it's drawn as a cylindrical tube. The area is pi r squared, d is the distance it travels. So I want the volume per unit time, and I say, well, the area is constant, but the material is moving, so what is the distance it covers per time? I just use the definition that the distance is equal to the speed multiplied by however long I'm measuring. So if I measured for 1 second, the speed was 12 meters per second, it would move 12 meters. If I measured for 2 seconds, it would have moved 2 times 12, 24 meters. So that distance is the speed multiplied by whatever time I measure. So put that in, and I have the volume that's passing my point P is, and I'm going to go back to saying area. I put the pi r squared because Chad said it, and it's correct. But area is simpler for me to work with. Area multiplied by V delta T. Now the flow rate Q is defined as, the volumetric flow rate, is the volume per unit time. So that would be AV delta T over delta T. And all of us are quite astute, and we can all say, wait, the delta T's cancel. So the volumetric flow rate, the amount of volume per unit time passing, is AV. Now it's actually on my next slide, so we'll have to wait on this and go to it. I'll just add one more thing. That's the volumetric flow rate. There is another kind of flow rate you might use. The mass flow rate, how much mass per time passes. What would be the relationship between the volumetric flow rate and the mass flow rate? Density. If I took that volumetric flow rate and multiplied by the density of water, then I would have the mass per time. We sometimes use the mass flow rate, sometimes the volumetric flow rate. But for a general physics class, the true will be fundamentally the same utility to us. Because for general physics, we're going to treat our fluids as completely incompressible. That is, we're saying that our fluids, no matter what pressure you put on it, you're going to have the same density. So if you have the same density regardless of the pressure, then the density never changes and you're just multiplying by a constant. So that's why there's no functional difference in our work. It's just multiply by density, divide out by density. Okay, now the actual continuity equation, if I have something that is changing its diameter, that means the area is changing. So over here, my flow rate would be Q1 is equal to A1 V1. Over here, Q2 is A2 V2. Now, just applying a little bit of logic, let us suppose that Q1 was bigger than Q2. That means I have more volume of water per unit time passing at point 1 than I have at point 2. If the water's not changing density, what would have to be happening? Not pressure. And if the density's not changing, because yeah, you would have a density change if you try to do that in real life. What would have to happen would be either A, I've sprung a leak, so some of my volume is leaking out, or B, somehow I'm storing water. So if we have a closed system here that's unbroken, we're not storing water, obviously not supplying water, then these two had better equal each other. So I had better have, I'll write up on top, just change color because I don't like that color. Q1 equal to Q2. The amount of water that flows in per second better equal the amount that flows out per second. So that means A1 V1 equals A2 V2. We call this a continuity relation because it is a principle of continuous flow of water. Now, if we have things like turbulence, which is where you create little vacuum bubbles, well, then you're not going to have this held true because you have those vacuum bubbles that are changing the effective density. And next class period, we'll learn about the difference in laminar flow and turbulent flow. Okay, we only have a few minutes left, so we won't get very far into Bernoullis Principle. But this picture here is a good introduction to the ideas of Bernoullis Principle. I have a car and a truck driving next to each other. And so the air, of course, has to move around the car and the truck. It doesn't go through it. And so the air splits around each vehicle, and you notice between the two, the spacing between those lines gets closer. When we look at a graph like this, the spacing between the lines tells us the speed of the air. When the lines are closer together, the air is moving faster. When they're farther apart, it's moving slower. So from this, you can say, if I look at the spacing here compared to the spacing here, sorry about that, the spacing was smaller in front and bigger in back. So if they drew this accurately, then the air is moving at a slower speed behind. I believe that's artistic error, but I'm just pointing it out. If instead I compare the spacing here to the spacing here, we see that they're much closer between the trucks, which means that it's traveling a lot faster. Bernoullis Principle, in a nutshell, actually, there is Torricelli's Principle, which is the Bernoulli taking away elevation. So it's more Torricelli's in this application, but Bernoulli's is the fundamental. Says that if you have a faster wind speed, the pressure drops. So that's why the pressure arrows are shorter in between than they are on the outsides. So you have a lower pressure between the two. If you're just in the car and you let go of the wheel, what happens in this situation? You get pulled into the truck. The same thing is true if you, I'm actually going to end with this story. If you are at a train and the train comes by, they have things that tell you to stand a yard back. It's not just because they're worried that you're going to lean in and get your arm hit. It's because if you're standing 6 inches away from the train as it comes by and it's going at speed, the lower pressure, because of the wind moving with the train on the train side, the higher pressure behind you is going to push you into the train. Now, this seems ridiculous. The story I'm going to tell is more ridiculous. When I was in graduate school, I spent 9 months working in the Department of Energy lab, and the government required us to have a safety lecture every month. And the scientists, dean scientists, didn't want to do it. They passed around a lead scientist for a research group had to provide one each month. They passed around who did it. The government didn't specify what your safety feature had to be. And so I was there to have a guy come in from the railroad company to give us a train safety lecture, because that's clearly going to help us in the Department of Energy lab, right? And in that, we saw all the videos of people doing silly things like standing right next to the track, the train comes by, and they get pulled in and beat up. And so, we went away with, wow, trains aren't safe. Good thing we don't have trains in the lab. Somebody, for the safety lectures, I wasn't there for this one, but somebody brought in a water ski safety guy to talk about water ski safety, because the government did not specify what the safety had to be about. Okay, have a good day, and I'll see you again on Friday. Really, it's Wednesday already?